It began more than 250 million years ago, after the most severe mass extinction the planet has ever known, an event so devastating that nearly all complex life in the oceans disappeared, and vast stretches of land were left stripped, quiet and uncertain. Forests collapsed across much of the world. Without trees to hold the soil, the ground loosened and washed away. Without plants, food chains unraveled from the bottom up. What remained was a planet missing its familiar signs of life, quieter than any era before it, and quieter than any era since. The Triassic did not begin with an explosion of new creatures. It began with emptiness. The climate offered little stability. Oxygen levels rose and fell. Carbon dioxide remained dangerously high, trapping heat in the atmosphere for millions of years. Global temperatures stayed elevated, never quite settling into balance. Above this unstable air stretched a single, immense continent. All of Earth's land masses were fused together, forming a vast supercontinent that reshaped climate in ways difficult to imagine. Inland regions lay far from any ocean influence, turning into enormous deserts larger than anything humans have ever known. Heat built up, moisture vanished, rainfall became unpredictable. Rivers disappeared for long stretches of time, then returned suddenly as violent floods, carving new paths through fragile land again and again. In this unsettled world, recovery was uncertain. Life did not surge forward. It hesitated, it adapted slowly, and often it failed. Many animals that survived the initial catastrophe vanished soon after, leaving no descendants behind. Survival did not guarantee a future. The creatures that would one day dominate the planet already existed, but only barely. They were small, rare, and easily erased, living as tentative experiments rather than assured successors. What followed was not a story of steady progress, but of repeated attempts, paths tried and abandoned. Survival is measured not by strength, but by endurance under constant instability. Even now, our understanding of this time continues to change, as new discoveries reshape old ideas and deepen the mystery. Tonight, we drift gently into this uncertain chapter of Earth's history. But before we begin, if you enjoy videos like this, slow, soothing, and quietly filled with wonder, I'd love it if you gave this one a like and maybe tapped subscribe. It helps more curious minds like you discover this peaceful little corner of the internet. And if you'd be so kind, let me know in the comments, where are you winding down from tonight, and what time is it there? It's always such a joy to see how far across the world these sleepy science videos reach. Now, take a deep breath, close your eyes, let your shoulders soften, and together, let's step softly into the Triassic world. Stone from the earliest Triassic does not greet us with abundance. It offers thin layers, broken traces, long stretches where nothing announces itself at all. In many places, rock that should hold evidence of thriving ecosystems instead preserves a kind of quiet, beds laid down without the usual signatures of complex life. This silence is not dramatic or sudden, it unfolds slowly, page after page of geological record, where familiar shapes simply do not appear. Fossils from this time tend to be small, scattered, and unevenly preserved. Instead of dense assemblages of shells, bones, or leaves, paleontologists often find isolated fragments, a tooth here, a trackway there, occasional impressions of simple plants clinging to unstable ground. Entire groups that once filled earlier rocks vanish almost completely, not replaced by new dominant forms, but followed by long gaps where only a few hardy survivors leave faint marks behind. The record feels thin because life itself was thin, stretched across landscapes that could not yet sustain complexity for long. This absence is not treated as a failure of discovery, it is evidence in its own right. When similar emptiness appears across continents formed from very different depositional environments, it suggests more than erosion or chance. It points to ecosystems so reduced that even under favorable conditions, little remained to be buried and preserved. Sediment continued to settle, rivers still laid down silt, seas still built layers of limestone, yet biological signals remained weak. The rocks speak quietly because the world itself was subdued. Within these deposits, scientists look for subtle patterns rather than spectacle. The distribution of certain hardy organisms, simple burrows, microbial mats, stress tolerant shell forms, reveals that life persisted, but at low diversity and low density. Survival can be traced through continuity, a lineage appearing before the collapse and reappearing afterward, even in diminished form, signals endurance. Recovery, by contrast, leaves different fingerprints. It involves diversification, expansion into new niches, and increasingly complex food webs that register clearly in the fossil record. In the earliest Triassic, those signs are largely absent. Instead, there are false starts. Species appear briefly, then vanish. Local ecosystems flicker into existence, only to collapse again when conditions shift. Fossil layers record repeated interruptions rather than sustained growth. This distinction matters because survival alone does not rebuild a world. It merely keeps a few threads intact, waiting for stability that has not yet arrived. Reading the silence in stone requires patience. It means accepting that what is missing can be as informative as what remains. In these early Triassic rocks, the scarcity of fossils does not mark a mystery waiting to be solved, but a reality waiting to be understood. Life was present, but it moved cautiously, leaving behind a record as fragile and restrained as the recovery itself. Long before the first signs of renewal could settle into rhythm, the surface of the planet itself had already changed shape. The land no longer existed as scattered continents drifting through separate climates and seasons. Instead, nearly all solid ground had drawn together into a single immense body, its edges surrounded by one continuous ocean. Its interior stretched far beyond the reach of coastal influence. This was not merely a rearrangement of maps, it was a reordering of how Earth breathed, circulated heat, and moved water across its skin. The scale of this union is difficult to grasp from a modern viewpoint. Distances from shoreline to interior spanned thousands of kilometers, creating regions where ocean moderation could no longer soften extremes. Winds crossed vast expanses of dry land, losing moisture long before reaching the center. Seasonal patterns amplified rather than balanced one another, with long periods of dryness broken by brief, intense wet phases. Geography became a force that acted slowly but relentlessly, shaping survival long before biology had space to respond. This unified landmass altered more than climate, it simplified pathways while removing others entirely. Migration routes stretched uninterrupted across continents that had once been divided by water, allowing certain animals to move farther than ever before. At the same time, isolation emerged in new forms. Inland basins became environmental islands, cut off not by seas, but by distance, heat, and the absence of reliable water. Life that entered these regions faced conditions unlike anything along the coasts, where moderation still lingered faintly. Mountains, formed during earlier collisions, influenced this new world unevenly. Some redirected winds and rainfall, creating narrow corridors of relative stability. Others cast long rain shadows, reinforcing dryness across enormous territories. Rivers began high, carved deep channels during brief flood seasons, then retreated for years at a time. The land remembered water even when it was gone, preserving channels that spoke of movement rather than constancy. For living organisms, geography now set boundaries before competition or adaptation could fully take hold. Proximity to the sea mattered more than latitude. Altitude mattered more than distance from the equator. Survival depended on finding pockets where conditions did not swing beyond endurance. The arrangement of the planet decided where recovery could begin, where it would stall, and where it would fail entirely. This rearranged Earth did not encourage rapid expansion, it demanded restraint. It favored mobility, tolerance, and flexibility over specialization. In many places, geography alone limited how far ecosystems could progress, regardless of potential. Life moved within the frame the planet provided, testing edges shaped by stone and distance rather than time. The Triassic world was not only healing from loss, it was learning how to exist on a surface that had become, quite literally, one world. At the far edges of the supercontinent, the air carried a faint memory of water. Along the coasts, winds arrived softened, shaped by long contact with the sea, still capable of releasing moisture with some regularity. These margins did not offer comfort, but they offered rhythm. Inland, that rhythm faded. With every step away from the ocean, the land slipped further from moderation, entering a realm where distance itself became a defining force. Moisture rarely traveled far across such an immense surface. Clouds lost their weight early, releasing rain near the coasts and mountain fronts, then thinning into dry air long before reaching the interior. The result was not a uniform aridity, but a deep imbalance. Long intervals passed without meaningful precipitation, broken only by short periods when saturated air finally crossed land and released its burden in sudden, destructive pulses. The ground absorbed little. Water rushed across bare surfaces, then vanished again, leaving behind erosion rather than nourishment. These inland regions became environments defined by inconsistency. Heat accumulated without relief. Seasonal swings sharpened, not because of latitude, but because of isolation from the sea's stabilizing influence. Nights cooled quickly, days intensified, and life endured stretches of deprivation that few complex organisms could tolerate for long. Survival depended less on adapting to a fixed climate and more on enduring repeated stress without breaking. In contrast, areas closer to the oceans experienced a narrower range of extremes. Temperatures still ran high, but they fluctuated less violently. Rain arrived more often, even if unpredictably. Shallow seas and coastal plains supported early chains of recovery, not through abundance, but through continuity. Small advantages, repeated over generations, allowed certain species to persist where interior counterparts failed again and again. This pattern reshaped the map of survival. Latitude lost much of its predictive power. Regions near the equator could be less hostile than temperate zones buried deep within the continent. What mattered most was access to moisture and the buffering influence of large bodies of water. The sea acted as a quiet regulator, storing heat, releasing it slowly, and feeding the atmosphere with vapor that life depended upon, even in limited amounts. Animals and plants did not spread evenly across this world. Populations clustered where conditions hovered just within tolerable bounds. Inland expansion occurred in pulses, often brief, often ending in retreat or disappearance when climate swung too far in one direction. Many lineages never established a lasting presence away from the coasts, leaving only sparse traces in the geological record. Distance from the sea quietly dictated which experiments in survival endured. Geography set the stage long before competition or innovation could matter. In the early Triassic, the ocean was not merely a boundary. It was an anchor, holding fragments of stability in a world still struggling to find its balance. Heat did not retreat when the collapse ended. It lingered, folded into the air and stone, carried forward through time rather than released. Evidence of this persistence appears quietly in chemical signatures, in altered minerals, in soils that formed slowly under warmth that refused to fade. The early Triassic world remained wrapped in elevated temperatures for millions of years, not as a brief aftermath, but as a background condition that shaped every attempt at recovery. This warmth was uneven, not gently distributed. Instead of settling into a stable global climate, the planet moved through sharp contrasts. Long, hot seasons stretched on without relief, followed by shorter intervals when conditions shifted abruptly. Temperature alone did not define these swings. The timing of rainfall, the length of drought, and the pace of seasonal change mattered just as much. Life encountered not a single challenge, but a pattern that rarely repeated itself the same way twice. Rocks from this period record these oscillations indirectly. Evaporite deposits appear and vanish. River sediments speak of sudden floods interrupting extended dryness. Growth patterns in early plants and shells reveal interruptions, moments when development paused or reversed. The climate provided warmth, but it withheld consistency, and this lack of predictability carried heavier consequences than heat itself. Organisms can adjust to high temperatures if those temperatures remain reliable. Metabolism, growth cycles, and reproduction can all recalibrate when conditions hold steady. What proved more difficult was a world where thresholds shifted constantly. Seasons lengthened or shortened without warning. Resources arrived late or not at all. Adaptations tuned to one pattern often became liabilities when the rhythm changed again. In this environment, recovery advanced unevenly. Populations expanded during brief windows of stability, then declined when those windows closed. Ecosystems failed not because they were weak, but because they were unfinished. They had not yet developed the buffers needed to absorb repeated disruption. The climate did not erase progress outright, but it rarely allowed it to consolidate. This explains why the fossil record shows persistence without momentum. Life remained present across the planet, yet diversification moved slowly. Predictable warmth could have supported steady rebuilding, but fluctuating conditions instead favored generalists capable of enduring variation. Specialists struggled to maintain footholds when the ground beneath their assumptions kept shifting. Over time, the importance of predictability became clearer than absolute temperature. Slight moderation in seasonal extremes opened space for continuity, not because the world became cooler, but because it became more reliable. In the early Triassic, climate acted less as a barrier and more as a moving boundary, constantly redrawn. Recovery waited not for comfort, but for patterns stable enough to be trusted, and that trust took far longer to return than heat did. Breathing itself became a negotiation with the world. The air of the early Triassic was not empty, but it was unsettled, carrying less assurance than it once had. Its composition shifted subtly over long stretches of time, enough to influence how bodies moved, how quickly they tired, and how much energy could be drawn from each breath. Life did not merely live within this atmosphere, it was shaped by its limits. Oxygen levels during the early stages of recovery remained lower and more variable than in later eras. This did not make life impossible, but it narrowed the margins within which complex activity could persist. High energy movement became costly. Sustained exertion drained reserves quickly. For animals accustomed to richer air, even simple tasks demanded greater efficiency or longer periods of rest. The atmosphere quietly selected against excess. These conditions altered the balance between body plans. Large size alone no longer conveyed advantage. Bigger bodies required more oxygen to fuel muscles, circulation, and growth. Without a dependable supply, size could become a burden rather than a strength. Smaller forms, with lower absolute demands, often operated closer to balance, able to persist where larger organisms struggled to maintain activity. Physiology mattered more than appearance. Respiratory efficiency, circulation patterns, and metabolic pacing determined survival far more than raw mass. Creatures with slower metabolisms conserved energy. Those capable of extracting more oxygen from each breath or delivering it efficiently through the body gained subtle advantages that accumulated over generations. These traits did not announce themselves dramatically in the fossil record, but their influence shaped which lineages endured. Activity patterns shifted in response. Bursts of movement replaced sustained effort. Growth slowed. Recovery between exertions lengthened. Even predators adjusted, favoring ambush and timing over pursuit. The air did not prohibit life, but it discouraged waste. It rewarded restraint, patience, and internal balance. Plants responded differently, yet were bound by the same atmosphere. Gas exchange through leaves governed growth rates, water loss, and resilience to stress. With fluctuating oxygen and carbon dioxide, photosynthesis advanced unevenly. Vegetation spread cautiously, shaped by air chemistry as much as by soil or moisture. The pace of greening remained slow, reinforcing the feedback between atmosphere and life. Over time, these constraints influenced evolutionary trajectories. Lineages that could function comfortably within narrow physiological margins persisted, even if they appeared modest or unremarkable. Others, built for abundance that no longer existed, faded despite surviving the initial catastrophe. The atmosphere did not act as a sudden filter, but as a continuous pressure applied day after day. In this early Triassic world, the air defined possibility. It placed ceilings on activity and growth, gently steering life toward forms that fit its quiet requirements. Recovery unfolded not only across landscapes and climates, but within lungs, blood, and cells, guided by an atmosphere that set limits long before dominance could return. Long after the collapse, the land lacked a quiet stability it had once taken for granted. Beneath open skies, the surface remained loose and unfinished, shaped by time but not yet held together. Soil, which normally accumulates through steady cycles of growth and decay, formed only slowly. Without dense plant cover to trap sediment and feed microorganisms, the ground stayed thin, easily disturbed, and reluctant to mature. Early Triassic soils tell this story through their absence as much as their presence. In many regions, layers that should record long periods of surface stability instead show repeated breaks. Hard surfaces appear briefly, then vanish beneath fresh sediment. Minerals weather unevenly, suggesting exposure followed by rapid burial, then exposure again. These are not signs of quiet landscapes. They speak of ground repeatedly reset, never quite allowed to settle into continuity. Erosion carved the land with particular urgency. Wind lifted fine particles and carried them away, stripping nutrients before they could accumulate. Water, when it arrived, moved fast across bare surfaces, cutting channels rather than soaking in. Slopes slid, floodplains shifted. In some places, ancient river deposits stack abruptly, each one interrupting the last, a record of motion rather than persistence. The land remained active, not because it was alive, but because nothing anchored it in place. Vegetation plays that role in stable worlds. Roots bind soil, slow erosion, and create sheltered spaces where microbes and insects can thrive. In the early Triassic, plants returned unevenly and often sparsely. Small pioneers clung to favorable patches, but forests lagged far behind. Without continuous plant cover, soil formation remained patchy, and land life faced a surface that offered little support. Animals living on land encountered constant challenges. Burrows collapsed easily, nesting sites disappeared, food sources shifted with every disturbance. Even organisms capable of enduring heat or drought struggled when the ground beneath them refused to remain predictable. Movement became costly across unstable terrain, and long term occupation of a single area proved difficult to maintain. These conditions reinforced a cycle of fragility. Sparse vegetation limited soil development, and weak soils limited vegetation in return. Each interruption reset progress, forcing ecosystems to begin again from modest foundations. The result was not lifelessness, but hesitation. Life occupied the land, but lightly, without the density needed to buffer change. Through erosion patterns and immature soils, the Triassic landscape reveals a world still learning how to hold itself together. Stability did not return all at once. It arrived slowly, in fragments, carried by the gradual spread of plants and the quiet work of time. Until then, the land remained without anchors, a surface in motion where survival required flexibility as much as strength. Recovery on land began quietly, close to the ground. Before forests could return, before shade or deep root systems altered the surface, a handful of hardy plants reclaimed space in fragments. These were not lush canopies or dense woodlands, but scattered pioneers, seed-bearing forms, and tough survivors capable of enduring heat, dryness, and poor soil without collapsing under stress. Early seed plants held an important advantage. By enclosing their offspring, they reduced dependence on consistently wet conditions. Seeds could wait, they could endure unfavorable seasons and germinate when brief windows allowed. This flexibility suited a world where rainfall arrived unevenly and soils offered little reliability. Alongside them grew other resilient plant groups, low and sparse, spreading slowly across disturbed ground rather than transforming it outright. Their presence began to change the land in subtle ways. Roots, even shallow ones, caught loose sediment and slowed erosion. Fallen material accumulated in small amounts, feeding early soil organisms and encouraging chemical processes that weathered rock into finer grains. These changes unfolded gradually, barely visible at first, yet they altered how water moved across the surface and how heat was stored and released near the ground. As plants spread, they influenced the atmosphere close to the surface. Transpiration returned moisture to the air, softening extremes locally even as the broader climate remained unstable. Carbon cycling resumed in fragmented form, with vegetation acting as a modest sink rather than a sweeping force. The land did not cool dramatically, but it began to behave differently, holding structure where it had once remained exposed. Despite this progress, forests lagged far behind. Building a woodland requires more than tolerant species. It depends on deep, persistent soils, reliable water access, and enough stability for trees to grow slowly over many years. In the early Triassic, those conditions remained rare. Droughts interrupted growth, floods undermined roots, fires, fueled by dry material and heat, reset patches before maturity could be reached. The result was a mosaic rather than a blanket. Vegetation clustered in favorable zones, near watercourses or regions where erosion slowed. Between these patches, vast areas remained sparsely covered, with plants present but unable to dominate. This uneven spread limited the pace at which soil could deepen and ecosystems could interlock. Plants were reshaping the planet, but they were doing so cautiously. Each gain depended on survival through repeated disturbance. Forests, with their long timelines and heavy investment in structure, required patience from a world that had not yet learned consistency. Plant recovery did not fail, it simply advanced in stages, laying groundwork rather than delivering completion. Through roots, leaves, and seeds, the land slowly regained its ability to hold together. Not all at once, and not evenly, but enough to shift possibility. The first plants to return did not restore the past. They prepared the surface for what might come next, long before the trees could follow. Below the surface, recovery followed a different rhythm. While land struggled visibly, the oceans carried their own delays, quieter but no less profound. Water retained the memory of collapse longer than the air or soil. Heat lingered in layers, chemistry shifted slowly. Circulation patterns that once moved nutrients across vast distances weakened, leaving large regions starved even as life attempted to return. Marine fossils from the early Triassic reflect this hesitation. Reef builders remained scarce. Shelled organisms appear unevenly, clustered in limited settings rather than spread broadly across seafloors. Many familiar groups survived only as reduced forms, smaller and simpler than their predecessors. Diversity remained low not because life had vanished, but because stability had not yet re-established the conditions needed for complex communities to persist. Chemical traces preserved in marine sediments reveal ongoing stress. Oxygen levels in deeper waters fluctuated, sometimes dropping low enough to exclude all but the most tolerant organisms. Stratified seas prevented mixing, isolating surface productivity from the depths below. Nutrients became trapped or unevenly distributed, interrupting the flow of energy that healthy food webs require. The sea remained present and full, yet internally fragmented. These conditions shaped how marine ecosystems rebuilt themselves. Instead of broad, layered communities, early recovery favored simple chains. Microbes and small plankton dominated large areas, forming the base of food webs that rarely extended far upward. Predators existed, but in reduced roles, limited by the scarcity of reliable prey. Each link depended heavily on the one below, leaving little redundancy when disruptions occurred. Storms and temperature shifts further unsettled these fragile systems. Periodic warming events altered circulation, sometimes expanding oxygen pore zones, other times briefly restoring mixing. Each change reset progress in different regions. Some shallow environments stabilized temporarily, only to be disrupted again when conditions shifted. The fossil record preserves this unevenness as a patchwork of promise followed by absence. Coral reefs, long pillars of marine abundance, illustrate this delay clearly. Structures that once anchored entire ecosystems remained rare for millions of years. Without reefs, coastal food webs lacked complexity and protection. Sediments shifted more easily. Habitats changed shape from season to season. The sea offered space, but not yet structure. Recovery beneath the waves required more than survival. It depended on circulation returning to reliable patterns, on chemistry finding balance, on energy moving smoothly from sunlight to the deep. Until then, marine life persisted cautiously, occupying limited niches and leaving faint traces behind. The oceans did not fail to recover. They moved at a pace shaped by depth, heat, and slow chemistry. Their story during the Triassic is not one of absence, but of delay, a long waiting period beneath the surface, where life endured without yet regaining its former complexity. The shift unfolded quietly, without a single turning point. Across drying floodplains and unstable shores, certain bodies simply fit the moment better than others. Reptiles did not arrive as conquerors. They persisted, step by careful step, in environments that demanded independence from water rather than closeness to it. One advantage lay beneath the skin. Scales reduced water loss, slowing dehydration during long periods without rain. Internally, kidneys conserved fluids more efficiently, allowing activity to continue where moisture was scarce or unreliable. These traits did not guarantee success, but they widened the margin between endurance and exhaustion. On land that oscillated between brief abundance and long deprivation, those margins mattered. Movement also favored restraint. Many reptiles maintained lower resting metabolic demands, burning energy more slowly than amphibians of similar size. This efficiency allowed longer survival during food shortages and reduced dependence on frequent feeding. When prey became scarce or seasonal, reptiles could wait rather than wander, conserving strength instead of spending it. The most decisive difference unfolded during reproduction. Amphibians remained tied to water, their eggs vulnerable to drying and temperature swings. Pools and wetlands that once supported breeding cycles had become unreliable. Some vanished for years. Others arrived briefly, only to disappear before development could complete. Each failed season erased entire generations. Reptiles carried a different solution. Shelled eggs enclosed developing embryos, protecting them from desiccation and minor fluctuations in temperature. These eggs could be laid on land, hidden among debris or shallow soil, independent of standing water. This freed reproduction from the rhythm of floods and allowed populations to persist even when surface water became rare or unpredictable. Over time, this separation reshaped ecosystems. Amphibians did not vanish, but their range narrowed. They clustered near remaining water sources, constrained to environments that could still support their life cycles. Reptiles spread more evenly across landscapes, occupying dry uplands, seasonal plains, and transitional zones between extremes. Their flexibility did not make them dominant yet, but it made them reliable. Physiology reinforced this trend. Reptilian lungs and circulation supported longer periods of activity without continuous oxygen demand, especially under warm conditions where evaporation posed risks. Muscles worked within narrower energy budgets, favoring bursts of movement over constant exertion. These patterns aligned with landscapes shaped by heat, exposure, and uncertainty. None of this unfolded as a competition consciously won. It was an alignment between body and world. As vegetation remained patchy and water unpredictable, traits that reduced dependency quietly accumulated advantage. Amphibians remained present, ancient and resilient in their own way, but the ground beneath them had shifted. By the middle stretches of the Triassic, reptiles had become the more consistent occupants of dry land. Their success grew not from strength or speed, but from insulation against absence. In a world where water could not be trusted, independence became the most valuable inheritance. They did not arrive with spectacle or sudden dominance. Their presence first appears as a subtle shift in form, written into bones that stand a little straighter, joints that align with intention rather than sprawl. In a world still uneven and demanding, archosaurs emerged not as rulers, but as a different way of moving across land that refused to stay predictable. This group carried a structural change that quietly altered how bodies interacted with gravity. Limbs positioned beneath the body, rather than splayed to the sides, allowed weight to pass cleanly downward into the ground. Each step required less lateral effort, less wasted motion. Over long distances and uneven terrain, this efficiency accumulated value. Movement became smoother, more stable, and less costly in energy, especially across landscapes shaped by loose soil, shifting surfaces, and irregular slopes. Upright posture also changed how bodies breathed and balanced. With the torso lifted away from the ground, Lungs and internal organs experienced fewer constraints during motion. Circulation supported sustained activity without the constant compression that limited sprawling forms. Heat dissipated more evenly as bodies rose above hot surfaces. These advantages did not transform archosaurs into sprinters or giants overnight. They allowed consistency, the ability to move reliably through a world where sudden floods, droughts, and erosion reshaped pathways again and again. Efficiency mattered more than speed. In an unstable environment, endurance often determined success. Animals capable of traveling farther without exhaustion could explore new territories, retreat from degrading ones, and track scattered resources. Upright movement reduced recovery time between exertions, preserving energy for growth and reproduction rather than constant repair. Posture also influenced how archosaurs interacted with changing ground. When the land shifted underfoot, a vertical limb alignment offered better balance and reduced strain. Slopes became manageable rather than prohibitive. Uneven surfaces no longer forced constant adjustment through muscular effort alone. This stability allowed archosaurs to occupy transitional zones that challenged other groups, areas neither fully wet nor reliably dry. These structural traits spread quietly through lineages, refined over generations rather than introduced fully formed. Early archosaurs remained modest in size and role, sharing ecosystems with many other reptiles. Yet their anatomy suited the demands of a planet still rearranging itself. Where climates fluctuated and surfaces refused permanence, posture shaped possibility. This did not erase older body plans. Sprawling reptiles persisted, many thriving within their own limits. The rise of archosaurs was not a displacement, but a gradual rebalancing. Certain environments began to favor efficiency over flexibility, endurance over immediacy. Upright movement met those demands. In time, this quiet adjustment would ripple outward, influencing how ecosystems organize themselves around mobility and energy use. For now, archosaurs simply endured, stepping carefully through instability with bodies designed to waste less and carry more. In a world still searching for footing, posture became a form of resilience, and that subtle advantage reshaped terrestrial life long before dominance ever arrived. Their arrival did not announce itself. The earliest dinosaurs appear in the record as quiet shapes, narrow bones pressed into sediments already crowded by other lives. They do not stand out through size or abundance. Instead, they slip into view as one presence among many, easy to overlook amid the wider experiment unfolding across the land. Early dinosaur fossils reveal animals that were small, lightly built, and limited in distribution. They left footprints no deeper than their neighbors and bones that rarely dominate a layer. These were not apex forms shaping ecosystems. They occupied marginal roles, often living alongside relatives that were more numerous, more widespread, and better suited to the moment. In some regions, dinosaurs appear briefly, then vanish from the record altogether, not erased by catastrophe, but edged out by competition and changing conditions. Their rarity was not an accident of preservation. In places where the fossil record captures a broad slice of life, dinosaurs remain a minority. Other archosaurs, including heavily built predators and diverse herbivores, filled most ecological spaces. Many of these competitors grew faster, reached larger sizes sooner, or exploited available resources more effectively. Dinosaurs, by comparison, seemed restrained, their potential not yet aligned with the demands of the environment. Close relatives often outperformed them. Crocodile-line archosaurs, with robust bodies and flexible diets, flourished across floodplains and river systems. Other reptile groups diversified rapidly, experimenting with armor, elongated limbs, and specialized feeding strategies. These animals occupied dominant roles in many ecosystems, leaving dinosaurs in the background, present but peripheral. What distinguished early dinosaurs was not immediate success, but subtle difference. Their anatomy hinted at efficiency rather than power. Limbs positioned for sustained movement, hips arranged for balance, growth patterns that favored gradual development. These traits offered no short term advantage in a world defined by instability and competition. They did not allow dinosaurs to outcompete neighbors who matured quickly or defended territory aggressively. As a result, dinosaurs remained scattered and unassuming. They survived, but survival alone was common in this era. Many lineages endured without ever expanding. Early dinosaurs shared this fate, persisting quietly without reshaping their surroundings. Their presence did not yet reorganize food webs or landscapes. They adapted to what existed rather than transforming it. This period reveals an important truth about their story. Dinosaurs were not inevitable rulers, waiting for their moment. For millions of years, they existed as one option among many, often overshadowed by forms better matched to the present. Their early history is marked by restraint, patience, and obscurity. Only later, under different conditions, would their particular combination of traits begin to matter. In the Triassic, those traits were merely sufficient. The first dinosaurs passed through this world almost unnoticed, not because they lacked promise, but because the world had not yet learned how to favor them. Dominance during this time did not belong to those who would later become famous. The landscapes were shaped instead by animals whose names rarely linger in popular memory, forms that filled rivers, plains, and forests in ways that set the rhythm of daily life. These creatures define the structure of ecosystems, controlling energy flow, movement, and space, long before dinosaurs had any meaningful influence. Large predators, unrelated to dinosaurs, occupied the highest tiers. Many were heavily built archosaurs, some with armor, others with massive skulls adapted for crushing force rather than pursuit. They moved through territories with authority, their presence shaping the behavior of smaller animals and determining where herds could feed or rest. Herbivores, too, belonged mostly to other lineages. Stocky plant eaters browsed low vegetation, while others processed tougher material with jaws built for endurance rather than speed. These animals were not transitional placeholders. They were well adapted to the conditions of the time. Dinosaurs existed within these systems, but rarely defined them. They remained scattered, often restricted to specific habitats or narrow ecological roles. Where food webs were already occupied by efficient specialists, dinosaurs found little space to expand. Their body plans, still early in development, did not yet provide clear advantages over competitors who had already diversified and refined their strategies. Timing played a decisive role. Evolution does not reward potential alone. It favors traits that align with present conditions, not future ones. Many dinosaur characteristics that would later prove powerful offered little immediate benefit in a world governed by instability and entrenched competitors. Growth rates, reproductive strategies, and feeding behaviors did not yet outpace those of established groups. In some cases, dinosaurs matured more slowly or relied on resources already claimed by others. The fossil record reflects this imbalance clearly. Sites rich with life reveal communities dominated by non-dinosaur reptiles and synapsids, with dinosaurs present but peripheral. Even when dinosaurs appear alongside later dominant groups, they remain modest in number. Their presence resembles a background note rather than a central theme. This dominance by others reinforced itself. Successful groups expanded their ranges, diversified into new forms, and occupied ecological space more completely. Each expansion reduced opportunity for quieter lineages. Dinosaurs persisted within the margins allowed to them, surviving without reshaping the systems they inhabited. These patterns illustrate how constraint operates through timing. Evolution does not progress toward a predetermined outcome. It unfolds through intersections of chance, environment, and competition. Dinosaurs did not fail during the Triassic. They simply arrived early to a world already ruled by others, a world whose structures favored different solutions. Only when conditions changed, when dominant groups faltered and new space emerged, would dinosaur traits align with opportunity. Until then, they remained secondary participants in ecosystems shaped by creatures whose reign was real, effective, and temporary. Variation spread across the Triassic landscape like quiet improvisation. Bodies changed shape in small increments, then in unexpected leaps, as if life tested possibilities wherever space briefly allowed. Limbs lengthened or shortened, skulls broadened or narrowed, armor appeared and vanished. These were not coordinated advances. They were attempts, scattered and simultaneous, unfolding across animals and plants alike. New strategies emerged in response to stress rather than opportunity. Some species favored thickened hides and heavy plating, trading speed for protection. Others adopted elongated forms, slipping through crevices or shallow water to escape heat and predation. Feeding methods diversified, with jaws built for crushing, slicing, or filtering, each tuned to local resources that could disappear as quickly as they arrived. These designs reflected immediate pressures rather than long-term success. Most of these experiments did not last. The environment remained too unstable to reward specialization for long. A body plan that worked during one phase of climate or geography often failed when conditions shifted. Floodplains dried, temperatures swung, vegetation retracted or returned unevenly. Each change erased advantages that had only just begun to matter. The fossil record captures this as a mosaic of beginnings without continuations. Forms appear briefly, sometimes in surprising diversity, then fade without leaving descendants. Their disappearance does not signal weakness. It reflects how narrow the window for success could be. Survival required not just adaptation, but compatibility with a world that refused to settle. Evolution during this time lacked foresight because it always does. Traits were selected for their present usefulness, not future promise. A structure that conserved water or energy might thrive for generations, only to become a liability under altered conditions. There was no direction pointing toward eventual dominance, only feedback between body and environment, repeated again and again. This explains the abundance of forms that feel unfamiliar, combinations that would never reappear. They were not mistakes, they were responses. Life explored what worked now, knowing nothing of what would matter later. Some strategies relied on low metabolism and patience. Others favored rapid growth and early reproduction. Each found brief success somewhere before instability rearranged the landscape once more. Across this period, the planet functioned like an open workshop rather than a finished system. Ideas were tested in parallel, often redundantly, rarely refined. Only a few traits, those flexible enough to tolerate change without precise tuning, carried forward reliably. The Triassic became a proving ground where failure was common and persistence rare. Out of countless variations, only a narrow selection endured long enough to influence the future. Evolution did not march toward complexity or dominance. It wandered, paused, and retreated, shaped by circumstances rather than intention. What survived did so not because it was destined, but because it happened to fit a world still deciding what it would allow. Their rise did not reshape the skyline or alter the ground in obvious ways. It unfolded close to the surface, among stems, leaf litter, and shallow soil, carried by bodies small enough to pass unnoticed. Insects expanded quietly into spaces left open by collapse, filling gaps that larger animals could not reach or sustain. After the disruption, insects diversified rapidly. Their short life cycles allowed quick response to changing conditions. Variations appeared and disappeared within generations, testing forms that could exploit heat, dryness, and patchy vegetation. Wings spread some lineages outward, while others remained grounded, burrowing, chewing, or filtering their way through the remnants of earlier ecosystems. This expansion was uneven but persistent, proceeding wherever resources appeared, however briefly. As plants returned in scattered patches, insects followed closely. Some fed directly on leaves, stems, and reproductive structures, limiting plant growth in some places while encouraging resilience in others. More importantly, insects began to move pollen between isolated plant populations. This process did not require dense forests or stable seasons. It functioned in fragments, allowing plants separated by distance or disturbance to reproduce more reliably than wind alone would permit. Pollination reconnected landscapes biologically, even when geography remained broken. Below the surface, other insects performed quieter work. Detritivores processed fallen plant matter, breaking it down into smaller components that microbes could access. This accelerated decomposition in a world where decay had slowed due to sparse vegetation and unstable soils. Nutrients cycled back into the ground more efficiently, supporting new growth and encouraging deeper soil development over time. These processes strengthened feedback loops that larger organisms could not yet sustain. Plants stabilized soil locally. Insects accelerated turnover of organic material. Microbial communities expanded in response, further improving soil structure. Each step reinforced the next, creating pockets of resilience amid widespread instability. This did not restore complexity quickly, but it allowed continuity. Insects also occupied positions across multiple levels of emerging food webs. They consumed plants, fed on detritus, preyed on one another, and served as food for larger animals. This redundancy mattered. When one pathway faltered, others continued. Ecosystems gained flexibility not through size or strength, but through numbers and interconnected roles. Their small bodies required fewer resources and tolerated sharper fluctuations. Heat spikes, droughts, and floods that disrupted vertebrate populations often reset insect communities without eliminating them. Recovery followed swiftly, sometimes within seasons. This consistency helped smooth ecological extremes at local scales, even as broader instability persisted. Insects did not dominate through force or visibility. They stabilized systems by linking processes that would otherwise remain isolated. Pollination, decomposition, and nutrient cycling continued even when larger life hesitated or failed. By sustaining the groundwork of ecosystems, insects allowed other forms of life to persist nearby. Long before forests returned or large animals reshaped landscapes, insects carried the quiet labor of recovery. They did not lead the Triassic forward in dramatic strides. They held it together, patiently, at scales small enough to endure what the larger world still could not. Water did not return evenly across the land. Instead, it gathered itself into corridors, narrow paths where movement, life, and time converged. Rivers traced these routes through unstable ground, carving channels that shifted with seasons and storms, yet persisted longer than the landscapes around them. Along their banks, the Triassic found moments of continuity in a world still rearranging itself. Floodplains became places where the story of life lingered. During wet seasons, rivers spilled outward, spreading sediment across wide, low-lying expanses. When waters receded, they left behind layered records, fine silt, organic fragments, footprints pressed into soft ground. These settings captured traces that drier uplands erased. Bones settled gently, leaves accumulated, tracks hardened before they vanished. Much of what is known from this time survives because rivers returned again and again, even when the climate remained uncertain. Seasonality defined these systems. Long, dry intervals reduced channels to isolated pools, concentrating life and limiting movement. Then sudden rains transformed stillness into force. Water surged through beds that had lain dormant, redistributing nutrients and reshaping terrain in a matter of days. For organisms living nearby, this cycle brought risk and possibility together. Floods destroyed nests and burrows, yet they also created fresh habitat, new soils, and open ground free from established competitors. This rhythm favored adaptability. Species that could exploit both scarcity and abundance persisted along river corridors. Feeding strategies diversified. Some animals timed reproduction to rising waters. Others retreated to higher ground and returned once sediments settled. Plants anchored themselves where periodic flooding delivered moisture and minerals, tolerating burial in exchange for renewal. Each cycle reset the environment without erasing it entirely. Rivers also served as pathways through the supercontinent. In a land where extremes limited long-distance travel, waterways offered guidance. Vegetation clustered along banks, forming ribbons of habitable space across otherwise hostile regions. Animals followed these lines, dispersing genes, traits, and behaviors from one basin to another. Evolution flowed with water, not in straight lines, but in branching routes shaped by topography and season. These corridors linked ecosystems that would otherwise remain isolated. A species established along one river could expand gradually downstream or upstream, reaching new territories without crossing barren interiors. Over time, this connectivity influenced which lineages spread and which remained confined. Water dictated opportunity more reliably than climate or soil alone. The fossil record reflects this importance. Many early Triassic discoveries emerge from floodplain deposits where life lingered long enough to leave an impression. These are not random snapshots. They are reminders that survival often depended on proximity to moving water. Rivers did not stabilize the world, but they offered structure within instability. They carried nutrients, organisms, and time itself across a changing land. In doing so, they shaped recovery quietly, channel by channel, leaving lifelines etched into stone. As the sun climbed, the land hardened into glare and heat. Surfaces baked quickly, air grew thin and restless, and movement became costly. Across much of the Triassic world, daytime imposed limits that bodies alone could not overcome. In response, life began to shift its schedule rather than its shape. Activity migrated into the margins of light. Early mornings stretched longer, evenings deepened. Night offered cooler temperatures, steadier conditions, and brief relief from thermal stress. For many small animals, darkness reduced water loss and lowered energy demands, allowing movement without the constant risk of overheating. What could not be endured by day became manageable after sunset. This adjustment did not require new anatomy. It relied on behavior, on timing rather than transformation. Simple shifts in activity patterns opened access to food and space otherwise constrained by heat. Insects emerged in greater numbers under cover of darkness. Small reptiles and early mammal relatives followed, moving cautiously across ground that still held warmth without its extremes. Predation changed pace, favoring ambush and short bursts rather than prolonged pursuit. Evidence of early nocturnal behavior appears indirectly. Eye socket proportions, brain region development, and growth patterns suggest sensitivity to low light and reliance on senses beyond vision. These traits did not define entire groups, but they appeared often enough to indicate a broader trend. Night was becoming a refuge, not from danger, but from intensity. For plants, night altered interactions as well. Certain pollinators operated after dusk, extending reproductive windows beyond daylight hours. Moisture lingered longer on leaves. Soil retained coolness, slowing evaporation. These small changes created narrow advantages that accumulated quietly. Behavioral flexibility proved especially valuable in an unstable world. Unlike physical adaptations locked into form, behavior could shift rapidly as conditions demanded. An animal active at night during hotter periods could return to daylight activity when climates softened or habitats changed. This versatility reduced the risk of specialization becoming a liability when the environment shifted again. Living by night also redistributed pressure across ecosystems. Competition eased as species divided time rather than space. Resources lasted longer. Encounters became less frequent. This temporal partitioning allowed more organisms to coexist within limited habitats, buffering ecosystems against collapse without requiring expansion. Over generations, these patterns reinforced themselves. Offspring inherited not just traits, but rhythms. Development synchronized with cooler hours. Feeding strategies adapted to darkness. Sensory priorities shifted subtly, supporting continued nocturnal or crepuscular behavior without fully abandoning daylight activity. The Triassic did not turn the world upside down at night. It softened it. Darkness offered consistency where days could not. In choosing when to move rather than where, life found a path through extremes without confronting them directly. Behavioral flexibility became a quiet form of resilience, allowing survival through adjustment rather than resistance. By retreating from the harshest hours, organisms expanded their chances without altering the planet around them. Night became a space of persistence, where recovery continued gently, one cycle at a time, beneath a cooler sky. Energy became the quiet currency of survival. Every movement, every breath, every moment of growth carried a cost that could no longer be ignored. In the Triassic world, where conditions shifted often and resources arrived unevenly, the balance between intake and expenditure shaped lives more decisively than size or strength ever could. Metabolism set the pace. High energy bodies burned fuel quickly, supporting rapid movement and faster growth, but only when food and oxygen remained dependable. In harsh climates, that dependence became a liability. Long, dry intervals, sudden temperature swings, and patchy vegetation turned consistent supply into uncertainty. Organisms that demanded steady input often found themselves overspending energy they could not replace. Lower metabolic rates offered a quieter advantage. Slower energy use extended survival through lean periods and reduced the need for constant foraging. Activity could pause without immediate consequence. Growth stretched over longer spans, trading speed for persistence. These patterns aligned more comfortably with a world that rarely provided stability for long. Growth itself became a careful negotiation. Rapid growth shortened vulnerability to predators and environmental stress, yet required sustained resources. Slower growth reduced immediate needs, but prolonged exposure to changing conditions. No single strategy dominated everywhere. Success depended on how well growth rates matched local rhythms of availability and disruption. Smaller bodies often fit this balance more easily. With lower absolute energy demands, small animals could survive on modest intake and recover more quickly after stress. They heated and cooled faster, but their reduced mass limited total water loss and allowed shelter in narrow spaces. When environments fluctuated, flexibility favored those whose requirements remained easier to meet. Large bodies carried advantages in strength and reach, yet they magnified cost. More tissue required more oxygen, more food, more water. In stable worlds, such investments could pay off. In the Triassic, where long-term predictability remained rare, those costs accumulated risk. Many large forms endured briefly, then vanished when conditions shifted beyond their margins. These pressures shaped population dynamics quietly. Smaller species often rebounded faster after disturbances, reproducing sooner and stabilizing local food webs. Larger species recovered slowly, vulnerable to repeated interruptions before populations could fully reestablish. Over time, this pattern reinforced itself, favoring communities built from many modest contributors rather than a few dominant forms. Physiology adjusted in subtle ways. Fat storage, muscle efficiency, and activity timing all reflected attempts to manage limited energy. Growth spurts aligned with favorable periods. Dormancy or reduced activity bridged unfavorable ones. Survival depended less on maximizing output and more on avoiding waste. In this environment, winning did not mean thriving in abundance. It meant lasting without collapse. Smaller bodies, slower growth, and restrained metabolism provided buffers against uncertainty. These traits did not guarantee permanence, but they increased the chance of endurance when the world refused consistency. The Triassic did not reward extravagance. It favored balance, measured consumption, and bodies tuned to scarcity. Growing, burning, and surviving became intertwined processes, guided by energy budgets that quietly determined which lives continued and which faded away. Recovery did not move in a straight line. Just as ecosystems began to assemble themselves into fragile patterns, those patterns were disturbed again. The Triassic record carries these interruptions quietly, layered between moments of progress, subtle breaks that reveal a world repeatedly pushed off balance before it could settle. Sedimentary sequences show signs of disruption arriving in pulses. Layers that suggest soil stability and slow deposition are interrupted by abrupt changes in grain size, chemistry, or fossil content. In some regions, plant communities expand briefly, only to retreat. Animal traces appear, then thin out again. These shifts do not align with a single catastrophe, but with repeated stresses applied over long spans of time. Volcanic activity played a persistent role in this instability. Large igneous provinces remained active well into the Triassic, releasing gases and particulates into the atmosphere episodically rather than all at once. Each phase altered air chemistry, cloud formation, and temperature balance. Carbon dioxide rose during active periods, trapping heat and intensifying existing warmth. Sulfur aerosols followed, briefly cooling some regions while disrupting rainfall patterns elsewhere. The atmosphere absorbed these shocks unevenly, redistributing their effects across land and sea. These changes filtered down into ecosystems gradually. Vegetation responded first, as shifts in temperature and moisture altered growth rates and survival margins. Reduced plant cover weakened soils again, reviving erosion and disrupting food chains that had only just begun to reconnect. Animals dependent on stable breeding cycles or predictable resources found those expectations broken repeatedly. Marine systems felt these stresses as well. Changes in atmospheric chemistry influenced ocean circulation and oxygen levels, reinforcing stratification and limiting recovery below the surface. Each atmospheric disturbance echoed through the seas, delaying the rebuilding of complex food webs that depended on reliable energy flow. What makes these interruptions significant is not their severity, but their timing. None individually erased life. Instead, they arrived just often enough to prevent momentum from building. Ecosystems require stretches of calm to deepen connections, diversify roles, and buffer variation. In the Triassic, those stretches remained rare and brief. Stability kept slipping away because the systems underpinning it had not yet aligned. Climate, geography, vegetation, and atmosphere continued to operate out of sync. When one element steadied, another shifted. Progress in one region coincided with regression in another. Recovery unfolded unevenly, advancing in fragments rather than as a coordinated whole. This pattern explains why the Triassic feels extended and hesitant rather than dramatic. The planet was not locked in crisis, yet it could not escape disturbance long enough to consolidate gains. Life adapted repeatedly to disruption, but adaptation itself required energy that might otherwise have fueled expansion. Recovery persisted through endurance rather than acceleration. Each interruption reshaped the path forward, narrowing options and favoring resilience over specialization. The Triassic world continued, not because stability returned, but because life learned to endure its absence, holding form through cycles that refused to settle into quiet. Shorelines during this time did not stay in place. They advanced and retreated slowly, almost imperceptibly within a lifetime, yet decisively across generations. Sea levels rose and fell in response to shifting climate, tectonic movement, and the lingering heat stored within the planet. Coastal plains appeared, vanished, and reappeared elsewhere, reshaping the boundary between land and water again and again. These movements altered marine environments without drama, but with lasting consequence. Shallow seas expanded across continental margins during higher stands, flooding low-lying regions and creating new habitats over broad areas. When sea levels fell, those same regions drained away, leaving behind isolated basins, restricted lagoons, and stranded shorelines. Each change reorganized circulation patterns, nutrient flow, and the distribution of life along the edges of the continents. Isolation became a defining feature of many marine habitats. As seas retreated, shallow basins separated from open oceans, cut off by rising land or narrowing channels. Water within these pockets warmed more quickly, evaporated more readily, and exchanged oxygen less efficiently. Salinity fluctuated. Chemical conditions drifted. Organisms trapped within them faced pressures distinct from those of the wider seas. Some species endured by tolerating extremes. Others adapted locally, diverging from their relatives beyond the barriers. Evolution proceeded in fragments, shaped by separation as much as by adaptation. When sea levels later rose, reconnecting these habitats, only a portion of those lineages persisted. Many vanished upon re-entry into broader ecosystems, unable to compete or adjust quickly enough. Shifting shorelines also altered where life could gather. Productive zones moved laterally, rather than expanding steadily. Food webs reorganized as coastlines migrated, forcing predators and prey to follow or retreat. Coral communities struggled to establish continuity when suitable depth and light conditions kept changing. Shell-producing organisms tracked sediment type as beaches and seafloors rearranged beneath them. These fluctuations imposed constant pressure. Stability rarely lasted long enough for ecosystems to mature fully. Adaptations that proved useful in one phase became fragile liabilities in the next. Organisms faced repeated decisions dictated by circumstance rather than choice: disperse, endure, or disappear. The fossil record preserves these dynamics as alternating layers of marine and terrestrial influence, sometimes closely stacked, revealing how quickly conditions shifted. Marine fossils appear where dry land once existed, then vanish as sediments signal retreat. Life responded continuously, but without certainty. Evolution under these conditions favored resilience over refinement. Broad tolerances outperformed narrow specialization. Lineages capable of surviving isolation and reconnection endured more reliably than those dependent on stable environments. Progress came through persistence rather than expansion. Moving seas did not erase life, but they prevented comfort. By reshaping habitats repeatedly, they ensured that recovery remained uneven and contested. Along shifting shores, the Triassic oceans rebuilt themselves slowly, pressured by change that never fully paused, yet allowed survival to continue in motion rather than rest. They lived where the light rarely lingered and where notice brought risk rather than reward. Early mammal relatives moved through the Triassic world along its edges, inhabiting narrow spaces beneath vegetation, within burrows, and inside the quiet intervals left behind by larger animals. Their presence was modest, easily overlooked, yet persistent in ways that louder lineages could not manage. These animals remained small by necessity as much as by inheritance. Compact bodies reduced energy demands and allowed concealment within unstable landscapes. Short limbs and flexible spines supported movement through dense cover and confined spaces where temperature and moisture fluctuated less dramatically than on open ground. Size limited visibility, and in doing so, reduced exposure to predators that dominated daylight and open terrain. Adaptability defined their survival. Diets remained flexible, shifting among insects, plant matter, and whatever resources appeared briefly within reach. Teeth reflected this versatility, capable of processing varied foods rather than specializing narrowly. Activity patterns adjusted readily, with many individuals moving primarily at night or during cooler periods, aligning behavior with opportunity rather than habit. They did not challenge dominant animals directly. Instead, they avoided competition altogether by occupying roles others ignored. While large reptiles shaped landscapes and controlled major food chains, these small mammal relatives threaded between those structures, benefiting from the stability created by others without contending for prominence. Survival depended on remaining unremarkable, not superior. Physiology supported this approach. High reproductive potential allowed populations to recover quickly after disturbance, even if individual lifespans remained short. Insulation through early fur or fur-like coverings moderated temperature swings, conserving energy in cooler hours. Sensory systems emphasized hearing, smell, and touch over vision, favoring awareness in low light and confined environments. The fossil record captures them sparingly, not because they were absent, but because their lives unfolded in places less likely to preserve remains. Tiny bones scattered easily, burrows collapsed, soft soils shifted, Yet their continued appearance across long stretches of time suggests persistence rather than rarity. They endured quietly while many larger forms came and went. Their strategy worked because it aligned with instability. By remaining small, flexible, and behaviorally responsive, they reduced reliance on external predictability. When climates shifted, when vegetation retreated, when dominant species disappeared, these animals adjusted without requiring dramatic change. Their survival did not depend on holding territory or controlling resources, but on slipping through change with minimal cost. Over generations, this approach accumulated advantage. Traits refined for concealment, flexibility, and internal regulation carried forward reliably. While others rose and fell with shifting conditions, early mammal relatives remained present, never abundant, never dominant, but consistently there. The Triassic did not elevate them into prominence, yet it shaped their future. By surviving without dominance, they carried forward a strategy built for endurance. When the world eventually offered new opportunities, that quiet persistence would matter more than strength ever had. Recovery did not sweep the planet evenly. It unfolded in fragments, shaped by local conditions that either permitted continuity or refused it altogether. Some regions gathered life slowly and held it. Others remained sparse, repeatedly cleared of progress by heat, drought, or chemical stress. The Triassic world became a mosaic of differing tempos, where neighboring landscapes told very different stories. In areas where climate moderated slightly, where water lingered seasonally, and soils deepened enough to support plants, ecosystems began to stabilize sooner. These zones did not flourish dramatically, but they sustained presence. Populations endured across generations rather than restarting after each disturbance. Food webs developed limited redundancy. Losses occurred, yet recovery followed without complete collapse. Stability arrived not as abundance, but as reliability. Elsewhere, conditions remained too volatile. Extended aridity, extreme temperature swings, or chemical imbalance repeatedly erased progress. Vegetation failed to persist long enough to anchor soil. Rivers shifted courses too often to maintain floodplain communities. In these places, life appeared intermittently, leaving faint or non-existent traces before withdrawing again. The land did not reject life outright, it simply could not hold it. This unevenness explains why some fossil-rich regions seem to leap ahead in recovery, while others appear delayed by millions of years. The difference does not necessarily reflect biological readiness. It reflects opportunity. Where environments offered even brief consistency, life could build incrementally. Where instability dominated, survival remained provisional. The fossil record preserves this patchwork imperfectly. Some gaps represent true absence, landscapes that supported little complex life for long stretches. Others reflect conditions unfavorable for preservation rather than habitation. Acidic soils dissolved bone, high-energy environments scattered remains before burial. In upland regions, erosion removed layers entirely. Missing fossils do not always signal missing life. They indicate places where continuity, whether ecological or geological, failed to accumulate. These absences themselves carry meaning. When large regions show prolonged silence across multiple lines of evidence, they suggest ecosystems too fragile to persist. When nearby regions preserve rich, continuous records, they reveal pockets where recovery found footing. Together, presence and absence outline the uneven contours of a planet healing without coordination. Species responded accordingly. Lineages fragmented into regional variants, thriving locally while remaining rare or absent elsewhere, dispersal slowed as suitable corridors narrowed. Evolution proceeded in parallel across separated landscapes, each shaped by its own limits. Some adaptations proved broadly useful, others remained confined, never spreading beyond favorable zones. A patchwork Earth favored flexibility. Organisms able to move, endure variability, or exploit temporary stability gained advantage. Those tied to narrow conditions found success only where geography allowed it. Over time, this uneven recovery filtered the future, preserving traits compatible with unpredictability. The Triassic did not rebuild itself as a single system. It emerged as a collection of systems, loosely connected, unevenly paced, and differently preserved. Understanding this mosaic brings clarity to its long recovery, a process guided less by uniform progress than by where stability happened to linger. Survival often hinged on where a life happened to exist when conditions shifted, not strength alone, nor innovation, but placement in space and time determined which lineages endured. A river that flowed slightly longer, a basin that cooled a little sooner, a ridge that captured rare rainfall could tip the balance between continuation and disappearance. The Triassic world rewarded coincidence as much as adaptation. Geography shaped outcomes unevenly. Species occupying regions buffered from extremes gained time to adjust, even if their traits offered no special advantage elsewhere. Others, equally capable, vanished simply because they lived where drought lingered longer or heat intensified more sharply. These differences did not reflect merit, they reflected circumstance. Across the planet, pockets of relative calm existed beside zones of persistent stress, and survival tracked those boundaries closely. Timing compounded these effects. A lineage arriving in a region during a brief window of stability could establish itself, while another arriving a few thousand years earlier or later failed under identical conditions. Recovery unfolded in waves that did not synchronize globally. Opportunities opened and closed without pattern. Those present at the right moment moved forward, those absent left no trace. Random events layered atop these patterns. Floods reshaped habitats abruptly. Volcanic pulses altered air and water chemistry without warning. Storms erased local ecosystems while leaving neighboring ones intact. None of these forces selected deliberately. They applied pressure unevenly, favoring neither complexity nor simplicity consistently. Survival became a matter of exposure rather than excellence. This randomness explains why success was not earned evenly. Some groups with seemingly modest abilities endured across vast spans of time, while others with advanced traits vanished quickly. The fossil record preserves these imbalances without apology. Lineages persist not because they were superior, but because they avoided the worst moments or encountered them with slightly more room to absorb loss. Evolution during the Triassic followed no guiding path. It responded to immediate pressures without anticipation. Traits beneficial under one set of conditions became neutral or harmful under another. There was no correction for injustice, no mechanism to reward effort. Progress emerged from accumulation, not intention. Over long periods, chance filtered possibilities. Survivors carried forward traits that happened to align with repeated disturbance. Not because those traits aimed toward future dominance, but because they allowed continuation through unpredictable change. In this way, randomness acted as a shaping force, narrowing outcomes through repeated testing rather than directed improvement. The Triassic reminds us that history is not built solely by the strongest. It is built by those who persist through coincidence, through narrow escapes, through alignment with moments that briefly allow survival. Geography, timing, and randomness intertwined to shape which lives continued and which ended silently. In a world still unsettled, chance was not an exception. It was a constant presence, guiding survival without fairness or direction, leaving behind a record defined as much by where life happened to be as by what it happened to become. Stability announced itself gently, not through abundance, but through repetition. Certain patterns began to return often enough to be trusted. Seasons followed familiar paths. Temperature swings softened at their edges. Extremes still occurred, yet they arrived within bounds that no longer reset the world each time. The Triassic climate did not settle quickly, but it began to behave in ways that allowed continuity to form. Over long spans, evidence of moderation appears in sediments and growth patterns. Soils deepen incrementally rather than being stripped away repeatedly. River systems show fewer abrupt abandonments of their channels. Chemical signatures suggest that atmospheric inputs fluctuated within narrower ranges. These are not signs of comfort, they are signs of reliability, a quiet shift from constant disruption toward usable consistency. With moderation came predictability. Wet and dry seasons still alternated, but their timing steadied. Organisms could align growth and reproduction to these rhythms without facing immediate reversal. Plants extended roots further into the ground, confident that soil would remain long enough to reward the effort. Animals adjusted movement and breeding cycles to seasonal cues that no longer shifted without warning. Ecosystems responded by thickening rather than expanding. Instead of spreading rapidly across new ground, life reinforced what already existed. Food webs added layers. Redundancy increased. Losses could occur without unraveling entire systems. Insects, plants, and microbes continued their quiet labor, but now their work accumulated rather than being erased. Nutrient cycles closed more fully. Energy moved with fewer breaks. Marine environments reflected similar changes. Circulation patterns grew more consistent. Oxygen levels stabilized across broader depths, supporting more complex interactions. Reef-building organisms, long absent or fragile, began to establish longer-lasting structures in select regions. These formations did not dominate the seas, yet they endured, signaling that conditions could now support extended cooperation between species. What mattered most was not any single improvement, but their alignment. Climate, soil, vegetation, and water began to operate within compatible ranges. When one shifted slightly, others absorbed the change rather than amplifying it. This coordination allowed ecosystems to hold shape through disturbance rather than collapsing outright. The fossil record records this moment not as a sharp boundary, but as a gradual thickening of continuity. Assemblages persist across layers. Species ranges extend without constant interruption. Absence becomes less pronounced, replaced by steadier presence. Life no longer appears only in flashes. It lingers. This stability did not erase the marks of earlier struggle. It built upon them. Traits refined under instability now functioned within calmer frameworks. Flexibility remained valuable, yet it no longer served as the sole defense. Structure returned alongside it, allowing specialization to begin cautiously once more. The Triassic world had not transformed into permanence. It had found balance sufficient to sustain itself. Ecosystems began to hold, not because disturbance vanished, but because it lost the power to erase progress repeatedly. In this quiet moderation, the groundwork for future acceleration settled into place, anchored not by triumph, but by continuity. Change arrived without announcement, carried in small accumulations rather than sudden leaps. The Triassic world did not pivot overnight into abundance. Instead, diversity began to rise quietly as conditions aligned just enough to support continuity. New forms appeared alongside older ones, not replacing them immediately, but adding layers where there had once been gaps. Complexity increased through overlap. Multiple species began to occupy similar spaces without immediate collapse, each drawing from slightly different resources or operating at different times. Plants diversified modestly in form and function, extending coverage across landscapes that had long remained open or unstable. As vegetation persisted longer, it supported a wider range of insects, which in turn fed small vertebrates and other consumers. These additions did not transform ecosystems dramatically, but they thickened them. Food webs strengthened through redundancy. Where earlier systems depended on narrow chains, newer ones allowed energy to travel along multiple routes. A loss at one level no longer unraveled everything above it. Predators gained alternative prey. Herbivores fed on a broader selection of plants. Decomposers worked continuously rather than episodically. This interconnection buffered disruption, allowing systems to absorb stress without complete failure. Marine environments reflected similar changes. Plankton communities diversified, supporting more consistent, higher level feeding. Shelled organisms expanded in variety and distribution, contributing to steadier nutrient cycling along seafloors. Reef-like structures remained limited but more persistent, anchoring localized diversity where conditions allowed. These developments were uneven, yet their direction remained clear. What distinguished this phase was momentum. Once continuity held for longer intervals, each gain reinforced the next. Soil supported plants more reliably. Plants stabilized climate locally. Insects linked reproduction and decay more efficiently. Vertebrates followed these frameworks, finding space within systems that now retained structure across generations. Acceleration did not mean speed, it meant fewer reversals. Evolution responded to this steadiness by exploring variation more confidently. New combinations persisted long enough to be tested across seasons rather than erased immediately. Some traits failed quietly, others integrated into existing networks. The rate of disappearance slowed as much as the rate of appearance increased. Survival became less precarious. Importantly, no single group drove this change alone. Acceleration emerged from interaction rather than dominance. Each layer depended on those below it remaining intact. This cooperation was not intentional, but structural, shaped by compatible timing rather than competition alone. The fossil record captures this phase through denser assemblages and longer species ranges. Gaps narrow, patterns repeat. Presence becomes more informative than absence. Life no longer appears only in brief interruptions between disturbances. It occupies time as well as space. This moment did not represent triumph or completion. It marked transition. The Triassic world had not become predictable, but it had become resilient enough to carry momentum forward. Complexity no longer dissolved at the first challenge. Diversity did not reset each time conditions shifted. Life began to accelerate because the world finally allowed it to keep moving. Not quickly, not dramatically, but steadily, guided by systems strong enough to hold progress without losing it again. Subtle signs appeared first, easy to overlook against the momentum already built. Growth continued, ecosystems held, yet beneath that continuity, the background signals began to shift. Chemical traces in sediments drifted from earlier patterns. Seasonality sharpened slightly. Variability crept back into systems that had only recently learned consistency. Environmental warning signs emerged unevenly. In some regions, temperature ranges widened again, stretching wet and dry seasons farther apart. In others, rainfall arrived out of phase, breaking the rhythms that plants and animals had begun to follow. Soils thinned where vegetation faltered under renewed stress. These changes did not arrive as a single event. They accumulated quietly, layered over what had seemed stable. Atmospheric conditions also changed. Periodic increases in volcanic output altered the balance of gases once more, introducing pulses of heat and chemical disruption that ecosystems struggled to absorb smoothly. Carbon inputs fluctuated. Aerosols interfered with precipitation patterns. The effects were regional rather than global at first, yet their reach expanded with time. Stability, though not lost entirely, became less reliable. Marine systems reflected this re-emerging tension. Circulation patterns shifted subtly, reducing oxygen availability in some basins while intensifying stratification in others. Productive zones contracted or migrated, forcing food webs to adjust again. Organisms that had settled into newly established roles faced altered conditions without warning. Some adapted, others declined quietly. What made this phase distinct was its timing. Stress returned after systems had begun to integrate. Complexity now meant vulnerability. Interdependence increased efficiency, but it also allowed disruption to propagate more widely. A shift affecting one layer rippled through others more readily than before. Recovery, once gained, now required protection. Instability reemerged not as collapse, but as erosion. Gains slowed. Diversity plateaued in certain regions. Extinction did not surge immediately, yet the balance tipped toward caution once again. Adaptations refined for moderate conditions became strained at their edges. Flexibility regained importance as predictability weakened. This pattern reveals a central truth about the Triassic. Recovery was never guaranteed. It depended on alignment between climate, geography, atmosphere, and biology that could not be permanently secured. When that alignment loosened, progress faltered. Not erased, but challenged. Life responded by adjusting rather than retreating outright. Some lineages narrowed their ranges, others shifted timing, diet, or behavior to compensate. These responses preserved continuity temporarily, but they also signaled constraint. The environment was testing resilience once more. The Triassic did not conclude with sudden reversal at this stage. It entered a period of renewed uncertainty layered atop earlier success. The warning signs mattered because they revealed how fragile recovery remained, even after millions of years. Stability had been earned cautiously, and it could be strained again. This return of stress reminds us that recovery is a process, not a destination. In the Triassic world, progress and pressure coexisted, with neither fully prevailing. The path forward remained open, but no longer assured, shaped once again by conditions that refused to stay still. Loss returned without the scale of the earlier catastrophe, yet its selectivity made it no less consequential. Groups that had persisted through prolonged instability now faltered. Certain dominant reptiles vanished. Many specialized marine organisms disappeared from records that had only recently regained density. The world did not empty again, but it thinned in ways that reshaped what remained. This extinction unfolded differently from the collapse that opened the Triassic. It was not a near total erasure of complex life, nor did it dismantle entire ecosystems simultaneously. Instead, it acted along fault lines that had formed during recovery. Lineages dependent on narrow conditions suffered most. Those occupying marginal climates, restricted habitats, or tightly coupled food webs found little room to adjust when stress intensified. Survival favored breadth rather than resilience alone. Terrestrial ecosystems lost several once successful groups that had dominated earlier landscapes. Their decline created open space rather than silence. In marine environments, turnover altered community structure more than sheer abundance. Certain long established forms vanished, replaced by others better suited to shifting chemistry and circulation. The seas reorganized rather than emptied. The decisive nature of this loss lay in its timing. Recovery had progressed far enough to build complexity, but not far enough to distribute it evenly. When extinction arrived, it filtered lineages that had gained advantage during instability but struggled under renewed fluctuation. Those with flexible physiology, broader diets, or adaptable reproduction endured. Others, refined for narrower success, faded from the record. Unlike the earlier collapse, this event did not stall evolution broadly, it redirected it. Pathways closed permanently, not because life failed to recover, but because alternatives now moved forward unopposed. The disappearance of certain competitors allowed remaining groups to expand without repeating earlier experiments. Evolution became less tentative. Environmental drivers contributed without repeating earlier extremes. Volcanic activity, sea level change, and climate shifts played roles, yet their combined impact targeted rather than universal. Stress accumulated until thresholds were crossed for some groups and not others. The result was differentiation rather than devastation. This extinction mattered because it finalized patterns that had been provisional. It resolved long-standing contests by removal rather than competition. Traits that had lingered in balance with others now defined ecosystems alone. The future narrowed, not in possibility, but in direction. The fossil record after this point carries fewer redundancies. Lineages stretch forward with less overlap. Forms that endured did so not by chance alone, but by compatibility with a world that continued to change. Recovery no longer reset, it advanced. This loss marked an ending that shaped beginnings. It closed the Triassic's era of experimentation and instability-driven turnover. What followed was not peace, but clarity. The world had selected, quietly and decisively, which survivors would carry complexity forward into the next chapter of Earth's long story. Survival across this boundary did not belong to the most dominant forms, but to those already accustomed to persistence under pressure. As the Triassic drew to a close, a quieter group of lineages carried themselves forward, not triumphant, but intact. They crossed into the next era without spectacle, bearing traits shaped by long exposure to instability rather than sudden success. Among terrestrial animals, certain archosaurs endured, including early relatives of crocodilians and dinosaurs. These were not the largest or most imposing creatures of their time. They were adaptable, efficient, and capable of functioning across a range of environmental conditions. Their bodies tolerated heat, dryness, and variation without precise dependence on any single setting. This tolerance mattered more than power. Small mammal relatives also passed through. They lived in the margins, avoiding competition by remaining inconspicuous. Their survival depended on flexible diets, shelter-seeking behavior, and reproductive strategies that did not require stable or expansive habitats. They endured not by resisting change, but by slipping through it. In the seas, continuity followed similar patterns. Groups with broad environmental tolerance and flexible life cycles persisted where others failed. Certain fish lineages, shelled invertebrates, and planktonic organisms crossed forward because they could survive variable oxygen levels and shifting currents. Their presence maintained the foundation of marine food webs even as surface communities reorganized. The traits that mattered most shared a common theme: efficiency over excess, flexibility over specialization, reproductive strategies that allowed rapid recovery after loss, physiologies that functioned under uneven conditions. These were not new traits. They had been refined over millions of years of interrupted recovery, tested repeatedly by instability. Continuity through catastrophe depended on carrying forward systems rather than peaks. Lineages that survived were those embedded within networks capable of rebuilding around them. Their disappearance would have fractured essential processes, so their persistence mattered not only to themselves, but to the structures they supported. This continuity did not preserve the Triassic world intact. It preserved its momentum. Survivors carried with them ecological roles, physiological solutions, and interactions that could be recombined under new conditions. The next era would not need to start from absence again. It inherited scaffolding. The fossil record reflects this passage quietly. There is no abrupt return to emptiness. Instead, familiar forms extend beyond the boundary line, joined gradually by new variations. Assemblages change composition rather than resetting entirely. Life continues, altered but unbroken. The importance of these survivors lies not in what they became immediately, but in what they allowed. They formed the bridge between unstable recovery and future expansion. Without their endurance, the next chapter of life would have required another prolonged rebuilding phase. The Triassic closed not with silence, but with transfer. Through stress and loss, continuity held just enough to move forward. Those who crossed did so without dominance, carrying resilience shaped by a world that rarely allowed certainty. Uncertainty lies woven into the Triassic itself, not as a flaw in understanding, but as a feature of the world it records. Even after decades of study, large stretches of time remain thinly represented, compressed into scattered fragments of stone. These gaps are not evenly spaced. They widen and narrow unpredictably, reflecting a planet whose preservation of life was as uneven as its recovery. In many regions, the record breaks entirely. Layers that should contain evidence of ecosystems instead hold little more than mineral traces or eroded surfaces. Entire environments passed without leaving durable remains. In some cases, life was sparse. In others, conditions simply failed to preserve it. Heat, erosion, chemical imbalance, and shifting landscapes erased what once existed before it could be sealed into rock. What we do not see is often as influential as what we find. Where fossils are present, interpretation is rarely singular. Similar assemblages can imply prolonged stress or brief disruption followed by recovery. Absence can signal ecological collapse or preservation bias. A sudden appearance of diversity may reflect genuine expansion or a change in sedimentation that captured life more effectively. Each layer invites multiple readings, none fully complete on its own. Competing interpretations arise naturally from this complexity. Some reconstructions emphasize delayed recovery and chronic stress. Others highlight resilience and gradual rebuilding. Both draw from the same evidence, yet frame it differently depending on scale, region, and assumed continuity. The Triassic accommodates these tensions because it was not uniform. It unfolded differently across the planet, resisting any single narrative that claims total coverage. This resistance extends beyond data into expectation. The Triassic sits between more dramatic chapters, preceded by the greatest collapse and followed by the rise of iconic dominance. It is tempting to frame it as mere transition, yet the evidence refuses that simplicity. It shows progress alongside fragility, innovation paired with erasure, stability emerging only to be strained again. What remains uncertain is not whether life recovered, but how unevenly and under what constraints. The timing of key changes shifts depending on location. The importance of specific drivers varies with perspective. Even the boundaries between phases blur as new discoveries revise timelines once thought fixed. Each fossil adds clarity locally while complicating the broader picture. This uncertainty does not weaken understanding, it deepens it. It reveals a period shaped less by linear progression than by overlapping processes unfolding at different speeds. It reminds us that Earth does not move in clean chapters. Its history accumulates through partial records, incomplete signals, and stories that resist compression. The Triassic remains difficult because it reflects a world learning stability rather than possessing it. Its evidence records attempts more often than outcomes. Its gaps speak of fragility as much as survival. In resisting simple stories, it preserves a more faithful account, one shaped by contingency, imbalance, and slow alignment. What remains uncertain is not a failure to know, but a reminder of how the planet actually changed, unevenly, imperfectly, and without obligation to clarity. Influence does not always announce itself through spectacle. The Triassic shaped the future quietly, by setting conditions rather than displaying outcomes. What followed depended less on what dominated during this era than on what endured through it. The world that emerged afterward carried the imprint of choices filtered slowly, traits refined under pressure, and systems tested repeatedly before being allowed to persist. This period mattered because it rebuilt foundations. Recovery did not restore what had been lost. It assembled new frameworks from fragments, assembling soils, climates, food webs, and physiologies capable of holding continuity. These frameworks carried forward, shaping how later ecosystems formed, diversified, and stabilized. The Triassic did not create the future directly, it made the future possible. In this way, recovery functioned as groundwork rather than triumph. Progress arrived without resolution. Stability emerged without permanence. Each gain remained vulnerable, requiring reinforcement over long spans. This caution shaped the biology that followed. Lineages learned to function within variability rather than ideal conditions. Success became associated with endurance rather than dominance, flexibility rather than excess. Later expansions built upon these lessons. When life diversified more dramatically in subsequent eras, it did so atop systems already capable of supporting complexity. Nutrient cycles closed more efficiently. Reproduction adapted to uncertain timing. Physiology tolerated wider ranges of temperature and oxygen. These were not sudden innovations. They were inherited solutions, carried forward from a world that demanded patience. The Triassic also shaped tempo. Evolutionary change learned restraint here. Rather than racing toward specialization, it lingered in forms capable of adjustment. This restraint allowed later radiations to proceed without immediate collapse. Momentum accumulated because restraint had been practiced first. Instability remained a constant presence throughout the Triassic, and that presence taught survival under imperfect alignment. Climate fluctuated, geography constrained, atmosphere stressed. Life responded not by waiting for perfection, but by persisting through misalignment. That persistence became a defining inheritance. As a lesson, the Triassic resists romantic framing. It offers no single hero group, no moment of sudden victory. Instead, it presents survival as a process shaped by endurance, timing, and accumulated tolerance. It shows that recovery is not a return, but a negotiation with what remains. The future was not written during this era, but its grammar was established. Limits were defined, pathways narrowed, systems capable of holding complexity were tested and retained. What followed moved faster because this groundwork had been laid slowly. The Triassic stands as a quiet architect. It shaped the world not by what it displayed, but by what it allowed to continue. Through patience under instability, through survival without assurance, it prepared life for expansion without repeating collapse. Its legacy is subtle, but profound. Not a chapter of triumph, but of preparation. Not an ending, but a careful beginning, carried forward by those shaped to endure a world that rarely stayed still.